All right, thank you, Howard. So my name is Steve Moore. I'm senior engineer with Atlantic Testing Laboratories. Just a little bit about myself. Been with ATL for about 15 years. Okay, I'm showing my screen, so hopefully everybody can see my screen now. Been with ATL for about 15 years. Wear a lot of different hats here at ATL, but a lot of what I do is concrete evaluations by destructive, non-destructive test methods. Today we're going to be talking about non-destructive test methods. So here's an outline of what we're going to be talking about today. We'll start with a definition of non-destructive testing, talk about some different purposes for NDT investigations. Kind of the meat and potatoes is the NDT methods. ACI 228.2 is a report on non-destructive test methods for evaluation of concrete structures. There's a whole bunch of different test methods that it talks about there. We're certainly not going to have time to talk about all of those, but we'll talk about a handful of them. And then at the end, we'll talk about estimating concrete strength using some non-destructive test methods. ACI 228.1 talks about a bunch of different number of different non-destructive methods of estimating concrete strength. A couple of ACI documents for reference estimating concrete strength. The ASTMs we'll be discussing to estimate the strength are C803, 805, and C597. So NDT, non-destructive testing, I think in our minds, we all kind of know what that is. The ACI definition is a non-invasive means of determining certain conditions or properties of materials. There's another body, ASNT, which is the American Society of Non-Destructive Testing. ASNT deals mainly with steel, I think, but they've got a different definition. It's testing for discontinuities or differences in characteristics without destroying the serviceability of the system. So if we think about NDT in that regard, you could consider taking a concrete core out of a slab or a wall or something like that as being non-destructive, depending on where you extract the core, because you might not be destroying the serviceability of the system. But for today's seminar, we're not going to consider coring as non-destructive. We're just going to focus on those methods that don't make Swiss cheese out of a floor slab. So the purpose of the investigation is really going to dictate what the proper test method is. There's a lot of different test methods, as I mentioned, and depending on what you want to find out for your investigation is really going to dictate what the proper test method is. Maybe you've got no record drawings of a certain structure. You don't know how much reinforcement is in there, what the size of the spacing is, or anything like that. Maybe you don't know what the original design strength is or was. Maybe you've got low compressive strength that you need to evaluate, or maybe you just want to do some, just kind of a general condition survey to figure out, is my structure sound? Is the concrete sound and durable? Do I need to do some rehab, or can I use the existing structure for for my design or to keep it in service? So certainly different purposes for NDT. These are a bunch of the methods that ACI 228.2 talks about. We're not going to talk about all of these. I'm not going to read all of these off. There's 12 or 15 of them here. Down here at the bottom, you can see there's about 20 more. If everyone can see, I'm going to use my mouse cursor to kind of point out some things. But again, we're not going to talk about all of these today. We're only going to talk about a handful of them. They're all going to be what we call the stress wave methods. Most of those are highlighted in red, and all the ones that are highlighted in red are stress wave methods. spectral analysis of surface waves, that's a stress wave method, impedance logging. We're not going to talk about those. We're not going to talk in detail about cross-hole sonic logging, but I will say that cross-hole sonic logging, or CSL, is really just an application, a specific application of pulse velocity, ultrasonic pulse velocity testing. If anybody has any questions about CSL, you can certainly submit them via the chat function. But like I said, we're not gonna talk about that specifically. But again, it is just a specific application of ultrasonic pulse velocity. So these are the methods that we're going to be discussing. UPV, ultrasonic pulse velocity, the different echo methods, sonic, ultrasonic, and impact echo, impulse response, which is kind of an interesting test method. Can tell you a lot of different things. Ground penetrating radar, surface penetrating radar. We call it surface because it's really not, you're really not penetrating deep into the ground. Most people are probably familiar with GPR. And then the three highlighted bullets there, those are the three methods we're going to talk about for estimating concrete strength. Rebound hammer, some people call it the Swiss hammer. I've heard it called the Schmidt hammer. Windsor Probe, which is penetration resistance, and then an application for estimating concrete strength using ultrasonic pulse velocity. So I mentioned these are all stress wave methods. Stress wave is just a sudden pressure, impact, impulse on the surface. It can be done with a hammer. It can be a sound wave. It can be an ultrasonic sound wave. The ultrasonic pulse velocity is about 54 kilohertz. And we like these stress wave methods because they're relatively easy to understand, and I say relatively. We're not talking about gravitational waves or the theory of relativity or anything like that. We're talking about sinusoidal waves. They've got some, they've got a period to them, and we've got some known input values. Maybe we know the force of the stress that's being applied. Maybe we know the frequency. Maybe we know the exact time that the stress was applied, or maybe we know all of those. So basically, we're taking some known input values from these different stress wave methods, and we're just trying to come up with some other values that using some algebraic formulas for wave theory. So some fundamental theories that ACI 228.2 talks about. The first one's pretty important. The stress wave propagation or wave propagation through concrete. You can think of it as analogous to sound traveling through air. So if you're in a room and you're talking, your sound is bouncing off the walls, off the ceiling, everything like that. Those sound waves are gonna behave a little bit differently than if you were to go outside and start talking or hear noises outside or even underwater or something like that. The idea is, these stress waves that we're putting into the concrete structures, it's going to bounce off of the bottom of the slab or the other side of the wall or something like that, or some other anomaly or defect within the slab itself. So if you're close to the edge of a slab, that sound wave is going to bounce off of the edge of the slab and maybe the bottom of the slab also. So sometimes you want to stay away from those edges and interfaces like that. So just always remember sound traveling through air. Excuse me. And the propagation speed depends on the density and the elastic constants of the concrete. These are Poisson's ratio, density, your modulus values, so that the wave speed is all depends on those elastic constants within the concrete. And then basically what we're doing is we're making conclusions or inferring certain things, making conclusions on the physical properties and conditions based on the resultant wave data. So whatever inputs we're putting in, we're getting some outputs, we're collecting some data, and then we're making some conclusions based on that data that we're collecting, either the wave speed or the frequency or you know, time-based information or something like that. So here we've got question number 1. Question 1 should be true or false. Wave propagation through concrete is similar to sound traveling through air. Please log your answer.
Okay, Steve, you can continue.
So hopefully everybody got that correct. That is true. Wave propagation through concrete is similar to sound traveling through air. So first method we're going to talk about is ultrasonic pulse velocity. It's I think it's probably the oldest concrete NDT method. There's a standardized method for it, Astm C597. You've got an ultrasonic transmitter, 54 kilohertz, and you've got a separate receiver. And basically you're measuring the travel time of an ultrasonic pulse across a known distance. And you're trying to figure out what that wave velocity is through the concrete. Really good for testing uniformity of concrete. And as I said before, it forms the basis for cross-hole sonic logging. So this is an image out of ACI 228.2. Over here to the right, you see we've got a separate transmitter. You know, consider this maybe an elevated slab or something like that. You've got a separate transmitter and then a receiver, and you've got a pulse that's being transmitted through the slab. We know the exact time that pulse started, and then we know the time the pulse was received, and we know the length or the thickness of the slab, and then we just figure out the velocity is just based on the length over time, distance over time, and we can figure out the velocity. So here on the left, we can see that our shortest travel time is going to be when we've got no obstructions, everything is, you know, well consolidated concrete, nice sound concrete. This is going to have the shortest travel time and give you the highest velocity for this particular case. You start to introduce maybe you've got some honeycombs or voids, or if you're doing CSL testing, maybe you've got a soil intrusion or something like that in your shaft. Your travel time is going to be a little bit longer, which is going to cause your velocity to be decreased. So you're going to have, you know, call it unsound concrete. You know, this other situation, maybe you've got a crack. The pulse has got to go around that crack. Obviously, that the distance is going to be longer. That L is going to be is going to be higher, so you're going to get a lower wave velocity. Or maybe you got a situation where you've got a transmitter, you know, you're transmitting a pulse on one side and you just don't even receive the pulse on the other side. You know, there's just some very large discontinuity in between there. So this is what the data looks like when we process it. Here we've got down here at T0 is when the pulse was transmitted. On the other side, it was received at about 92 microseconds. This is the first arrival. Here, this is the frequency. This is the pulse itself. If anybody wants to do the math, you can kind of count up the peaks and figure out the time, you know, over time and figure out the frequency, which should be pretty much 54 kilohertz. And what we're doing here is we're figuring out what the velocity is. So we know the time the pulse was generated, we know the time, or we know when it was received. It took 92 microseconds to receive the pulse on the other side. This particular slab was 18 inches thick. That gave us a velocity of 16,000, just over 16,300 feet per second, which is pretty fast. This was 5,000 psi concrete, and it was a 5,000 psi concrete mixed design. I think it was breaking at 65, 7,000 psi. So 16,000 feet per second is pretty high. 12 to 15,000 for 4,000 psi concrete is certainly not unheard of. 16,000 is pretty fast, though. But it implies that you've got nice sound concrete. So what can we use ultrasonic pulse velocity for? Like I said, concrete uniformity, finding voids, unconsolidated concrete, maybe in kind of poor concrete, evaluating the depth of fire damage. I'll talk about that in a minute. Estimating strength, we'll talk about that towards the end also. Velocity is proportional to the modulus, which increases with strength. I will say that that increase is not linear. So if you've got, say you've got 5,000, 4,000 psi concrete that has a velocity of 10,000 feet per second, a velocity of 20,000 feet per second doesn't mean that you've got 10,000 psi concrete. So that the increase in velocity is not get a linear increase with your strength. The results can be sensitive to moisture within the concrete. So younger concrete that may not be fully cured, you're going to get a different value. And probably the biggest downfall to ultrasonic pulse velocity is it really works best when you've got access to both sides of the concrete. You can do indirect methods to where you're doing it on the same surface, which is how we evaluate fire damage. You can do indirect methods to where maybe you're doing it on a square column and you're doing it on a face that's 90 degrees from the face where the transmitter is. But really, it works best when you've got access to both sides and you're on opposing faces. So when we use ultrasonic pulse velocity to evaluate fire damage, it's easy to understand. The damage layer has a lower modulus, and it's got a lower wave speed or slower wave speed than the underlying sound concrete. And when we test it, the stress wave travels along two distinct paths, which I'll show you visually here in a second. The first one is along the surface through the damaged concrete, and then the second path kind of goes through the damaged concrete across the sound concrete, and then is transmitted back up to the surface. And what we do is we vary the transducer spacing, and we plot that over time. So we start with here we've got the transmitter and the receiver. Here's our damaged concrete section, fire damage here at the top, sound concrete here at the bottom. When the transducer and the receiver are really close together, that first arrival time that we saw in that that prior graph that had the stress wave, the first arrival time is going to be across the surface of the concrete. That's going to be across the damaged surface of the concrete. So we record that. We increase the spacing, maybe by half an inch, maybe by an inch. You don't want to increase the spacing too much. And then we figure out what that wave speed is again. Eventually, as the spacing gets wide enough, the first arrival time, the path is going to take this path here that we see on path number 2. It's going to go through the damaged layer concrete, across the sound concrete, and then back up through the damaged concrete. And that's going to be the first arrival time. So as we make that spacing wider and wider, that travel time across path 1 is gonna increase, and the travel time on path 2 is going to decrease, or is going to be the shortest the shortest travel time. So what we do is we plot the transducer spacing distance and the travel time, and we get this line here for path 1, and eventually, as we space them out far enough, we'll get this for path 2. And to figure out the depth of the fire damage, we just use this kind of a modified point slope equation to figure out what the depth to the fire damage is. This is a bit of an idealized graph. I've done this a couple of times. It does work. I think the key is really to get that transducer spacing nice and tight, so you see this. The break in the slope of the 2 lines. So here we've got question number 2. Should read which stress wave method can be used to evaluate the depth of fire damage.
Go ahead, Steve.
All right, the answer is ultrasonic pulse velocity. Hopefully everyone got that. I'm kind of throwing up softballs here, so hopefully everyone's catching them. Next test method we're going to talk about are the echo method: sonic echo, ultrasonic echo, impact echo. Mainly going to focus on impact echo, but the theory is very similar for all of them. Basically, you've got an ultrasonic wave or some impact wave that's transmitted and received on the same surface. So that's the echo, right? The wave is reflected by flaws or discontinuities, and it's kind of a periodic wave. And what I mean by that is that it goes back and forth. So it'll go down, hit some discontinuity, get reflected back up. The surface is a discontinuity, so it'll get reflected back down, and it just goes back and forth, and that's kind of the echo. And there's a resonant frequency. There's a dominant frequency that's associated with that, and we process that. We figure out what that dominant frequency is, and we use that to figure out what the depth of the flaw is. That dominant frequency, some people call it a thickness frequency. It's inversely related to the depth. So as the frequency increases, the depth to your flaw, your discontinuity, actually decreases. And again, we can figure out what the depth is. Here we got a couple more images out of ACI. This is the pulse echo method, where you've got a single transmitter and receiver. Again, here's that echo. The reflection going back and forth. That's the periodic nature. This is the pitch catch method, which is probably the most common method. You got a separate transmitter and a separate receiver. There's also a phased array. I haven't used this. I've seen the equipment for it, and you can kind of, you've got multiple impacts and pulses and receivers, and it can kind of give you a mapped image of your flaw. So that's kind of interesting. But here you can see, I mentioned the periodic. You can see how it, the wave travels down, bounces off of some flaw or discontinuity, or maybe it's off of the bottom of the slab, goes back up to the top again, which is a discontinuity, and then goes back down to the bottom. So we get this these varying dominant frequencies depending on what's reflecting that stress wave. And the lower the frequency is, the deeper the flaw is. The higher the frequency, you've got this, that stress wave is, bouncing back and forth in a periodic nature. So here you've got a higher dominant frequency. To figure out what the depth of the flaw is, or whatever the reflecting surface, discontinuity flaw, whatever you want to call it. Figure out the wave speed. We talked about using pulse velocity for wave speed. The impact echo method also has a way to determine the wave speed. And then we know the resonant frequency. Once we plot it, we know what that resonant frequency is. And based on the wave speed, the resonant frequency, we can figure out what the depth to the flaw is, or the reflecting surface, if we want to know what the thickness of the slab is. And impact echo, that standardized test method, you can figure out what thickness of the slab is. You can figure out the depth to the flaws. It can be a little bit tricky. I'll go back to this to these diagrams here. Again, somewhat idealized diagrams. These peaks are not always easy to distinguish. You really gotta collect the data. Get good quality data. So you can really pick out these dominant frequencies. Some people find it hard to understand. You're plotting things in frequency domain. And using fast Fourier transformation, and looking at amplitude spectrums. And fortunately, the software takes care of most of that for us. But again, you really got to make sure that you're collecting good quality data in the field, so you can process it. So we're going to move on to the impulse response method. This also has a ASTM standardized test procedure. You've got an instrumented hammer and an adjacent receiver. That instrumented hammer has got a force gauge on it, so we know, strain gauge. We know the force. It's that's the force of the impact within the slab. It can be used to detect a number of flaws, anomalies within the concrete, immediately below the concrete. It's really, really good for finding voids underneath slabs. It can also be a little bit difficult to interpret and understand, but it can be very, very effective. Ideally, it works best when you've got a constant thickness. So a slab that's constant thickness, and I don't mean it's got to be exactly 6 inches. It doesn't work so well, maybe on abutments that are a little bit thicker at the bottom that they are on the top. That doesn't mean that it can't be used, because you've got a constant thickness across, across the bottom, horizontally across that abutment, most likely. But comparing data vertically, on an abutment that's thicker at the bottom than it is in the top may be kind of tricky. So again, we've got this hammer with a load cell, so we know the force that's going into the structure. We got a velocity transducer with geophone. We're figuring out the velocity, and what we're plotting is a value called mobility, which is a ratio of force and velocity at a specific frequency. You would typically plot the different mobility values on a contour plot, and this could be an image that maybe represents a slab, and maybe you've got some reinforcing here that's delaminating away from the concrete or something like that. So again, you're getting velocity from the geophone. We know the force that's coming from the hammer. There's a strain gauge or you know, in the hammer, so we know the force that's going into it. And then there's that mobility number, which is the ratio of the amplitude and force amplitude for a given velocity amplitude and force amplitude for a given frequency. And then we evaluate that for over a frequency up to about 1,000 hertz. And basically, you get like a flexural vibration in plate-like structures, if you can kind of think of it that way. So here's our mobility value, and you know, here's our frequency range. And again, at each of these frequencies, you know, there's that ratio of velocity and force. So we figure out what the average mobility is. Typically, what happens is you know, you start to get up in these higher frequency ranges, and the mobility just kind of tails off, you know, up and over to the right. So there's a little bit of engineering judgment on, you know, where in this frequency range to evaluate. That's kind of where the where the thickness comes in. You know, it's a little bit easier to evaluate if it's all if they're all constant thicknesses. But you get an average mobility value for a specific data point, which is one strike of that instrumented hammer. And when you plot them, you might get something like this. We saw this one already. Maybe you've got some delamination on reinforcing steel. Maybe this is a bunch of different data points, and you typically collect them on a grid like this, so you can make a contour plot. This could be a slab. Maybe we've got some curling on the edges along here. You know, there's some slab curling, and maybe we've got a void underneath the slab right here. So it's easy to visualize once you plot all of the mobility values. So again, you can kind of use it to detect voids beneath pavements, slabs, spillways, in kind of delamination around reinforcement. I've seen it used on bridge decks quite a few times, you know, to evaluate the condition of reinforcing steel, because you do get that debonding, you know, that delamination on the reinforcing steel, and that typically shows up really well. Poorly consolidated, voided concrete. I will say you got to have it has to be somewhat significantly voided. You know, small voids. You know, if it's kind of marginally consolidated, it may not. This may not be the best method. And you can use it to find debonding. You know, again, kind of delamination, really delamination of any. You know, of any layers. So we're going to get into ground penetrating radar. I'm going to guess most of the listeners are probably familiar with this. For concrete, we use it mainly to locate reinforcement. Very good at locating reinforcement in concrete. Pre-stressed tendons in you know, like T-beams or something like that for parking garages. Can be used to measure the thickness of slabs. It can be done with pretty high degree of accuracy if you can dial in the dielectric value. I won't discuss that too much, but every unique material, or every material, has a unique dielectric value. It changes with concrete if you can dial that in for the specific mix that you're scanning. And you get a good reflection off the, you know, at the bottom of the slab. You can figure out what the thickness is. You can also use it to detect voids beneath the slab. Interpretation a lot of times can be very, very easy, or it can be extremely difficult. And oftentimes, as with some of these other NDT methods, sometimes the data is inconclusive. So if you've ever seen GPR data for concrete, this is what you see. You know, you see a lot of these kind of parabolic reflections, and this parabolic reflection comes from really the travel distances from the reflected wave. So, you know, as you take the GPR and you scan it across the surface from left to right, you know, at this position, it's still detecting. It does detect this target. It just detects it at a longer distance, which is why it plots this D1 distance here. So as you get closer and as you get over the top of the target, your travel time is the least because it's closest to the surface, and you get the peak of the parabola right here. As you scan across on the backside of the reinforcement, it's still again detecting the reinforcement at this distance D3, which is represented here. So that's the reason for the parabolic shape, is it's just the different travel times and distances from the target that it's detected or detecting. So this is an actual scanned image. It can tell us a lot of different things. We see the you know, these parabolic reflections down here at the bottom. I've added in, you know, these circles here to kind of represent the reinforcement. Kind of think of this as an elevation view with the slab or concrete surface being at the top, and this is depth within the slab. And this particular scan is a slab. So you can kind of see down here at the bottom this dark reflection. That is the bottom of the slab. So if we've got the dielectric set properly, we can figure out what this slab thickness is. In this case, it was right about 12 inches. Some of the other things we can figure out is concrete cover. We know the peak of this parabola, that's where the reinforcement is. So again, if we've got our dielectric value dialed in for this particular mix, we can figure out what the concrete cover is. You know, we're about you know, about 10 inches down, maybe just under 10 inches down. So nice to see that. I don't think this is mesh, but a lot of times we'll see you know, we'll see that wire mesh just laying right here at the bottom. So we can also get rebar spacing, just kind of going peak to peak to figure out what the spacing is. And you know, this is 40 inches here, 45, 50 inches. So you know, we're just over 10 inches. You know, probably designed to be 12 inches on center or something like that. It might be a little bit different over here. But this is all good information we can get with GPR, slab thickness, concrete cover, rebar spacing. I will say that there's not a GPR unit out in that exists that can tell you what the size of the reinforcement is. So that's one thing that you can't get with GPR is what the size of the reinforcement is, which is unfortunate for most of us. So here we've got question number 3. And it should read, which stress wave method uses mobility plots to show anomalies?
Steve, please continue.
So which stress wave method uses mobility plots to show anomalies? That is impulse response. So these are the fundamental theories. This is the same slide from I don't know, maybe 30 minutes ago. You know, it talks about wave propagation analogous to sound traveling through air, and then got highlighted down there at the bottom. You know, inferences, conclusions. You know, physical properties can be made, you know, from resultant wave propagation data. So this is where we're using these inferences and conclusions to you know, these different constants, elastic constants, trying to relate them to concrete strength. So there's another ACI document, 228.1. Incidentally, ACI Committee 228 is the non-destructive NDT committee, so that's why 228.1 non-destructive methods to estimate concrete strength, 228.2, those are the different non-destructive test methods. So 228.1 talks about a lot of different in-place methods to estimate concrete strength. We're not going to talk about all of them today, but a lot of them are based on stress wave methods and some of the stress wave formulas and wave propagation that we've been discussing. So, you know, we're trying to relate compressive strength to elastic constants or results that we get from, you know, impacts or stress waves that you know, that we're putting into concrete. I want to stress that these methods should not be used as the sole method of acceptance. And all of these methods, they just give us estimated concrete strengths, not actual concrete strengths. The only way to get actual concrete strength is to take a core and to test the core. Because by definition, the concrete strength it's the ultimate strength. We're testing it to failure. We put it in a compression machine, we're squeezing it, and we're testing it to failure. Obviously, none of these methods are testing to failure. So they're just estimated methods. They're all based on standardized procedures. So that's not to say that, you know, they're no good, but they shouldn't be used as the only method of acceptance. Rebound hammer is probably the most common NDT method out there for estimating strength. Relatively easy to do. There's certainly some things to understand with the test method. Here's kind of an internal view of what's going on inside the rebound hammer itself. We've got this hammer or mass. We've got this spring, and then we've got a plunger here. So we push down on the rebound hammer, which engages this spring that's got a known spring constant and this mass that has a known mass. All of these rebound hammers are all standardized to the test method. Once the hammer reaches the surface, or the plunger reaches the surface, the hammer is released, and it goes down by the force of the spring. It bounces off of kind of the shoulders here of this plunger and rebounds back up, and that rebound number is what that's the data that we're collecting. And again, this is you know, there's lots of different manufacturers, or a handful of manufacturers of rebound hammers, but they all need to meet the same standard, so that, you know, basically all the numbers mean the same thing, or they're standardized numbers. Down here inside the concrete, you know, this is kind of showing, you know, just different things to be aware of. You know, there may be you know, maybe a large piece of coarse aggregate or something here. Maybe there's a void just below the surface here. Maybe you've got some, who knows, maybe this is fire damaged concrete right here, or right here, maybe you've got some surface imperfections. Maybe this is like a broomed finish or something like that. Each one of these situations is gonna impact the rebound number a little bit differently. You might get a higher rebound number because you're right over a piece of coarse aggregate here. You might get a lower rebound number because you've got a void, or maybe it fractures the surface right here. You might get very, very low rebound number because a lot of the energy, you know, is being absorbed in this, you know, softer, you know, fire damaged, if that's what it is. You know, either way, it's absorbing energy. And then same thing right here. You've got all these little ridges. You know, it's easy to understand that, you know, these ridges are going to absorb some of the energy and probably give you a lower rebound number also. So surface characteristics play a really big part in what the rebound number is. So when you're doing this test, if you're testing you know, a wall to a footing to a slab or something like that, you need to understand that each one of these you know, the surface characteristic is a little bit different. And if you're going to be comparing rebound numbers, you want to make sure that you're comparing apples to apples, make sure that it's the same mix, make sure the finish is the same. You know, whether it's a steel troweled finish or a formed finish or something like that. You want to make sure that you're comparing apples to apples because it does make a difference. So still talking about the rebound hammer, it's easy to understand. We've got an impact, we've got a stress wave on the surface, we're measuring that response. You know, we've got a stress-strain relationship going on. You know, the stiffness, that's basically what's being measured here. That rebound is the stiffness. As I mentioned, important to understand the energy transfer and the influences, whether it's surface preparations, aggregate beneath the surface, voids beneath the surface. Because those surface characteristics have a significant influence on the results of that rebound number. So we're going to move on to penetration resistance, Astm C803. Most people call it the Windsor Probe. You've got a hardened steel probe that's essentially shot into the concrete with, I believe it's a 32 caliber 32 caliber shell. It's not some shell you buy off of the shelf at Dick's or Sporting Goods store or something like that. It's very specific. It's got a known amount of energy, you know, based on how much powder is in there. You know, again, kind of easy to understand. You got a stress wave, you know, you got an impact on the surface. We're measuring the response. That response is the penetration depth. You know, the deeper it penetrates in the concrete, the weaker the concrete is, the stronger the concrete is, it's not going to penetrate so much. Some other things that influence, or one of the biggest things that influences the Windsor Probe is the aggregate hardness. And that could be a significant factor. So when we're doing this test in the field, there's a Mohs Hardness kit that goes out, and you know, it's got 9 different minerals, and it's just a scratch test on the aggregate. You know, it's either a 3 or a 4 or a 5 or something like that. Around here in you know, central upstate New York, we got a lot of limestones. You know, our Mohs value is usually right around 3 or 4. Surface characteristics much less influential with the Windsor Probe than with the Rebound Hammer. So here's a picture of the Windsor Probe. This is the instrument itself that shoots the probe into the concrete, and we measure the exposed length. There is a little bit, there's kind of a failure cone. You know, it can be argued that this is you know, maybe a slightly destructive test because it does, you know, it does penetrate the surface. Usually there's, you know, maybe a 2-inch, maybe 3-inch diameter surface. You know, it can usually be, you know, take some mortar or something like that, or you know, a Portland water mix and fill it in. But what we're doing here is we're measuring the exposed length, and then we go to different tables, you know, based on the Mohs hardness of the aggregate, and the you know, again, this is a standardized test method, standardized pin length, standardized energy going into it, and we go to a bunch of tables, and based on the exposed length, we figure out what the estimated concrete strength is. And again, the less exposure, that means that this probe went deeper into the concrete, and the concrete essentially is weaker or has a lower compressive strength. Last one we're going to talk about is ultrasonic pulse velocity for estimating concrete strength. This is what the equipment looks like. Again, there's, a separate transmitter, receiver. Over here on the right, you can see there's a calibration bar. We use this calibration bar basically every time we turn the unit on, we calibrate it. Something that's important to note that I didn't mention, you kind of see right here, there's this gel underneath this transducer. That's a couplant gel. It's important that you have that both the transmitter and receiver have good coupling with the concrete surface. So as we mentioned before, wave speed depends on elastic constants, or elastic modulus. It's proportional. The wave speed is proportional to the square root of the elastic modulus. The modulus is empirically related to compressive strength, but remember, it's not linear. It can be influenced by a number of different factors: moisture, carbonation. Carbonation actually densifies, hardens the surface a little bit. In that regard, Rebound Hammer can also be influenced by surface carbonation also. So again, ACI 228.1 in-place methods. Want to stress one more time, should not be used as the sole method of acceptance. All these methods are good to estimate the strength. A lot of them do a really, really good job of providing you relative strength. If you want to compare, one portion of a foundation wall to another portion of the foundation wall, maybe two different mixes, two different placements of the same mix. You're getting rebound numbers of 45 in one part of the wall. You're getting rebound numbers of 42 on another part of the wall. You can conclude that it has a relative, the compressive strength is relatively less than in the area where it was 45. How much less? Don't always know. So that leads us to question number 4. Which should be true or false. Non-destructive test methods can provide actual compressive strength.
Please continue.
Thanks, Howard. True or false, non-destructive test methods. Non-destructive tests can provide actual compressive strength. That's false. But if you remember at the beginning of the presentation, I talked about the ASNT definition of non-destructive testing. By their definition, depending on where you take a core, it could be considered non-destructive. But I think for the most part, we all consider coring as a destructive method. So some final considerations. Depending on why you're doing the investigation, you might want to consider validating some of the results with cores, probes, maybe some other minimally invasive techniques should be considered. It's always nice to have validation of data because these are non-destructive methods. We don't always know exactly what's going on inside the concrete. So it's always nice to get some kind of validation. You don't have to do it across the whole, project. But picking a couple of spots here and there, if you've got some anomalies that you identified, a whole bunch of anomalies, maybe verifying it with a probe or a core. Each method is a unique tool in and of itself. combining different test methods, impact echo with GPR, with Rebound Hammer or something like that. So combining a bunch of these test methods can provide us more information. So we often do that. We'll often combine test methods, just to have a whole bunch of tools in our toolbox rather than just one. And I think I mentioned it in the GPR. I can mention it with all of these NDT methods. The data and the results, they might be inconclusive at times. Maybe, again, we don't know exactly what's going on, or maybe we might not know what's going on. Maybe the data is not telling us the whole story. And there is a chance that some of these methods, all of these methods, may prove to be inconclusive. A lot of times when I get phone calls from clients or prospective clients, I spend more time talking about the limitations and what information they may not get versus what information they can get. So it's important to know that NDT doesn't always tell us everything. So for the most part, that's about it. If anyone has any questions, please submit them through the chat feature, and Howard will kind of compile those, and we can start addressing some of those. Are we seeing any come in, Howard? Howard, are we seeing any questions coming in?
Yes, we have a couple, and I'm trying to get them pulled up here, Steve. For impulse response mobility contour plots, what is the minimum void or defect size that can be resolved with a typical concrete slab?
Yeah, that's a good question. It's going to depend a lot on your grid spacing. So the finer your grid spacing, the smaller the anomaly that you can detect. But I would say for impulse response within the slab itself, not underneath the slab, but within the slab itself, you'd have to have something, some significant deterioration, like maybe tennis ball size. Anything smaller than that, and I'm not sure the impulse response would show much of a difference in that mobility. Now it's a different story underneath, because underneath now you've got kind of an unrestrained condition below the slab. Below the slab, you'd be able to see voids, voids below the slab that were smaller than a tennis ball size. And I guess I should clarify that a little bit. The void between the bottom of the slab and the ground would be smaller than tennis ball size, not the extent of the void in like a horizontal dimension. Hopefully that answered the question.
Is there an NDT method to know early strength of concrete?
There's a couple of NDT methods for early concrete strength. I would say the one that we see used most is the maturity method, and that uses kind of the time temperature history of curing concrete. But for that method, you have to establish a baseline typically in the laboratory. For maturity, you would have to have a baseline established in the laboratory. A lot of these other methods you could still use to evaluate early concrete. Ultrasonic pulse velocity is probably one that I wouldn't use to evaluate early age concrete, because that might give you some values that are a little higher than they really are, just because the early age concrete still might have a lot of moisture in it. It's still kind of green and curing.
Is there an NDT method to determine the size of rebar?
There is. There's an instrument called an R meter or a tachometer that induces a magnetic field into the rebar, and based on the size of that magnetic field, it can figure out what the cross-sectional area of the reinforcement is and give you size. I've used that a number of times. It won't work in a column because you've got a lot of large rebar very closely spaced together in a column, most of the time it comes back with a number 4 or a number 5 bar, but number 4 is probably the most common bar size out there. The easy answer is yes. But you have to understand how it works and the limitations.
What would be the most appropriate method for determination of slab thickness? For example, are there methods available that are able to determine thickness to an 1/8 inch tolerance?
Impact echo, ground penetrating radar, coring. I guess that's not non-destructive. GPR is used quite often, and impact echo, the standardized test method for impact echo you can use to get slab thickness.
Is there any method to detect corrosion in rebar?
There's a method called half-cell testing that you can evaluate the potential for active corrosion. Half-cell testing. But it doesn't tell you how much it's corroded or anything. It just tells you if it's it gives you the it tells you the probability of active corrosion based on the movement of electrons and stuff like that. It can be done. Any others?
That appears to be the last question.